start off, our talk is called Thermoptic Camouflage. I don't know who here is Ghost in the Shell fans. Woohoo, Ghost in the Shell! Anyways, so we thought the whole thermoptic camouflage thing, Ghost in the Shell, was awesome. Basically, it's like sort of invisibility suit, and it was a good title for the talk because we're talking about how you can make exploits invisible to your standard IDS or IPS. Quick introductions.
Yeah, my name is Brian Caswell. I am a principal research engineer for SourceFire. We do an IDS, IPS, and we're the primary developers of the Snort intrusion detection product. I am a Metasploit developer and a member of the SHMU group.
My name is H.C. Moore. I'm Director of Security Research at a company called Breaking Point Systems. We develop hardware that makes other hardware scream, and that's basically it. I'm also the founder of the Metasploit project and also a lead developer. So the plan for today, basically show you how to do evasion at every layer of the stack. Start off at layer 2, do layer 3, layer 4, and then all the different application layer protocols, and show really where the IPSs and IDS products are falling down. Some of the demonstrations we had planned today aren't going to work as well as we thought because the appliance I was going to bring with me as our sacrificial lamb wouldn't fit in my luggage. But we'll have demos anyways, but it won't be quite as cool. So the quick thing about evasion. The whole principle behind doing IDS or IPS evasion is you have to know more about your target than the IDS or IPS does. Whatever product you're trying to evade, you have to know more about the system you're attacking than it does. And that's how you can do things where it sees one attack, but you send another attack. And that's just basically, that's the basic rule. If you know your network better than the IDS does, you do things like abuse routing issues and TTL and asynchronous routes to make sure that the IDS doesn't have a clear picture of what's going on. Also, if you know your IDS really well, you know exactly what signatures it uses, how it does pattern matching, and what its weaknesses are, and you can abuse those things to also bypass the IDS or IPS. So kind of the evasion layers we're going to talk about today are, first of all, hardware, layer 1, layer 2. There's really not a whole lot there, and what is there isn't really relevant these days for internet-based attacks. Then we're going to go into operating system layer vulnerabilities, where, not really vulnerabilities, but differences, where fragmentation is different between different platforms, how you can abuse that. Some of that's rehashing, some of that's new. And finally, we're going to go into application layer attacks, everything from client-side security to DCRPC and SMB. First off, kind of layer 2 stuff. There's a lot of different ambiguities of the Ethernet layer. Depending on what card you have, it may drop a frame depending on if certain bits are set or if the length field's too long, or if you have multiple VLAN headers. It's all sorts of tricks you can do at the layer 2 level that'll cause an IPS to route the packet because it doesn't understand what it is, but may allow the target to actually process it anyways. And you can use things like broadcast destinations where the IDS won't process the broadcast or it will process the broadcast in a different way. There's lots of different tricks to use the Ethernet layer. We're not really going to go into it too much because at the layer 2 level, it's not really that practical. And even at a large organization, layer 2 attacks aren't that significant because you have to go through a router or a switch to get to your target.
The next layer up that we want to talk about is the OS modeling. The first people that really set the mark for IDS evasion was Paytech and Newsham. They released a paper a number of years ago. They talked about TTL evasion tricks. So if your TTL at the IDS, if a packet is going to drop dead midstream before it actually hits the host, what the IDS sees of the TCP stream is going to be different than what the host sees. They also talked about IP fragmentation differences between how they handle overlapping. Same thing with TCP fragmentation and then sequence issues. There's a number of other tricks that they talked about, different hosts and networking tricks, and then fake teardown sessions. So if you do fins mid-session that the host is going to ignore, but because they're off with sequence numbers, but the IDS will say, hey, there's a fin, I'm going to shut down the session. So the IDS thinks that the session is shut down, but the host doesn't. The host will continue on connecting that. That's kind of old history. So a little bit of overview of how fragmentation works. You take an IP packet and you split up into smaller chunks. So if an IP packet won't go across what the different network cards will support. So the minimum fragment size is 8 bytes. So each of the different IP stacks that are implemented all implement how they handle overlaps and duplicate packets and missing sections in the fragmentation differently. Well, one of the nice things is because they're all different, the IDS has to know what each of them do and how they handle it and how they handle each of these odd cases and put them back together so they know what the actual host is, when the data gets to the host, what's bad and what's not. And unfortunately, this is incredibly difficult, especially when the different versions of the different operating systems change how the fragmentation is handled. So not very long ago, Paxton and Hanley released a paper discussing a number of the different IP fragmentation models that were released. the popular ones they came out with. So they released this very simple model of how they handle that. So they send out 6 different packets. As you see them on the screen, they come in the order of 1, 2, 3, 4, 5, and 6. And these are overlapping and gapping fragments. So when you line them up, they're lined up so depending on how the operating system reassembles the fragments, they'll reassemble only into a chunk as big as a 12-byte chunk. So if we look at how BSD handles it, it's very simple. As the first packets that come in first, those are accepted, and then additional data is laid on top of that. BSD write, the same sort of thing, except if the data in a fragment that comes in afterwards, it contains a gap, they will overwrite where the gap is. In the same thing, Linux does something very similar to the BSD. And then you have Windows where it just takes the first fragment. It always takes the first fragment for any of the gaps that come in, ignoring everything else. At least that's what Paxton says. And then iOS handles it the exact opposite way. All the fragments that come in, they just handle them in reverse order. Whatever comes in last, they overlay that on top to get the 12 bytes. Well, unfortunately, that's not exactly how it works. So the way iOS handles it now is overlapping fragments are just dropped, which is probably the best way to handle it. There's no ambiguity.
Ambiguity.
Yeah, that word. You shouldn't see overlapping IP fragments in a real-world environment. So iOS, Cisco decided, hey, this isn't supposed to happen. If you see it, just drop it, because it's not supposed to happen in the real world. So they handled it correctly. So a couple of the other models that they had were not quite right. So one of the things that's interesting to know that for BSD, the way that BSD write actually works is if the fragment ends at the end of a buffer that already exists, then it will overlay that. It will only overlay it if it ends on a fragment that's already existed. And then Windows and Solaris their models are slightly different as well. It will only do the overlay, or it will also overlay if there's a gap, but one of the fragments totally supersedes one of the previous fragments. So as you see here, normally what was previously thought is where the 3.3 would exist, that was already seen, so we'll accept that, and then we'll overlay 5 before it and 5 afterwards. Well, what is truly happening, because the packet that comes across with the 4 5s, when that happens, it totally overlays on top of the 3, so those are overlaid and are just dropped. And there's a ton of different application modeling issues.
Okay. So one of the biggest things about application layer attacks and application layer evasion is for every single protocol out there, each vendor implements that protocol a little bit differently. Take something as simple as a web server, for instance. You do get/HTTP 1.0, and there's some spaces between the URL and your GET request and your HTTP version, and that's basically it, just starting with that. Depending on what vendor is, they may treat space characters as a different character. And we'll get into that a little bit later towards the end. But basically, depending on how the application is written, what characters it thinks spaces are, what characters it thinks line delineators are, it'll handle that packet differently. So as long as you know more about how that application reassembles or actually processes the stream you send it, as long as you know more about that application than the IDS does, you can make sure the IDS sees something completely different than what the application sees. Vendor-specific extensions are a large problem because anytime you add an extra extension to a protocol, say with the LDAP stuff as part of Active Directory, or the funky DNS stuff, and Rendezvous or Bonjour or whatever it's called these days, depending on what the IDS vendor does, they may not be able to process those extra extensions correctly, may not know what to do with them, and therefore any vulnerabilities in that protocol are hard for them to be able to detect at a protocol layer.
Yeah, another example is, for example, if you have IIS installed, it handles directory normalization in one way. If you have the front page extension, the front page extension only mapped to a certain directory inside IIS and exposed in a certain directory on the website, only in that directory will it be handling the reassembly and the conversion of directories as it's handled through the front page extension, but the rest of the website will be handled somewhat differently. So all of that has to be handled by the IDS, and most IDSs can't do that yet.
And just about every protocol out there, there's at least one trick you can play with. There's at least some trick you can do with it that, depending on what the application is, will handle it slightly differently. You want to cover sidestep?
Yeah. So the first real application evasion papers that were released was Robert Graham from ISS released Sidestep. It had a number of different IDS evasions and bypasses that he implemented. The primary ones that he discussed were SunRPC fragmentation. So at the TCP layer, you can fragment SunRPC requests. At the time, none of the IDSs actually had, except for Robert Graham's IDS, could handle that. Also, one of the interesting things that he also did was FTP. So everybody knows that Telnet has negotiation options. So what kind of terminal it supports, how does it handle backspace, how it handles tab, that kind of stuff. Well, FTP, because it's command line based as well, FTP also supported all of these Telnet options. So that was something else that he added in. So you could take a FTP login, add in the middle of my username, add in my escape character is this other thing. In the middle of the username, so the IDS has to understand that. He also added the HTTP URI encoding, so encoding a slash as the hex equivalent, encoding the dots as the hex equivalent as well. Again, there's a lot of very new techniques that we're going to discuss today, a lot of very vendor-specific URI encodings, some brokenness in the actual implementations of the protocols that most IDSs, if you read the RFCs, you're not going to, as an IDS implementer, you're not going to understand how each of the brokenness is handled. And then we're going to talk about some of the more deep protocols. And then we're also going to talk about some client-side attacks.
SMB, I mean, I'm assuming everyone here knows what SMB is, has heard of it before, that kind of thing. SMB is pretty basic. SMB is a generic transport protocol used by Windows and used by Samba for everything from file sharing, system administration, user account management, all sorts of things. RPC calls, DCRPC, everything goes over SMB in the Windows world for the most part. With the exceptions to that are the bare DCRPC protocols that go through their own wrappers. SMB-based vulnerabilities. If you're writing an IDS and you want to detect vulnerabilities using the SMB protocol, you have to look pretty deep. You have to look for things like malware propagating, like basically file rights with certain names and certain content. People actually accessing the registry service in a way that should be, looks like an attack. You have to be able to parse the registry protocol, which is actually a DCRPC application running on top of SMB. Authentication flaws, you see someone to log in with a username and a password that's usually used by a backdoor or installed as part of it, some kind of malware. You need to be able to decode the authentication credentials from the request. And finally, once you get into DCRPC, there's so many other vulnerabilities that people are looking for and need to be able to detect if you're an IDS vendor that it becomes very difficult to correctly detect those attacks if you have to parse SMB, DCRPC, and so on. So if you're an IDS developer, what do? The basic way is you create a signature for it. Say, I want this string. This attack has this string in it. For example, let's say you're trying to detect the LSAS vulnerability, where it's an overflow in a DCRPC service. You're looking for a certain string that's part of the exploit. Well, that works great until someone changes that string or uses TCP segmentation, DCRPC fragmentation, or SMB fragmentation, or SMB segmentation to bypass the stuff or do padding. That doesn't work very well. So then they go to state tracking and say, okay, what state is this protocol in? So I'm going to look for a signature in this packet, but only when the packet's in a certain state, like after the DCRPC bind request has been seen for this given UUID for this attack. And then they realize that doesn't work, because you can still do fragmentation, still do things to bypass it. Then they start doing state plus context tracking plus signatures. So they have to basically create an entire DCRPC state engine into their IDS to be able to properly track these requests and figure out where the vulnerabilities are. And once they get that deep into it, they become really application and operating system specific. If that operating system accepts some strange flag or works slightly differently than they think, you can still evade that signature. So the IDS vendors are really behind a rock and a hard place with regards to how to detect these attacks. But at the same time, all of the new attacks that we're seeing on the internet, like things like Blaster, things like the LSAS stuff that are being used by self-propagating malware, all of those use these protocols. So unless you can detect these attacks correctly, your IDS is basically